In Andy Weir's epic science fiction novel, The Martian, our hero Mark Watney is confronted with some incredible obstacles if he is to survive. One of the most significant that he faces almost immediately upon being abandoned on the Red Planet is the complete lack of water, and so Watney has no choice but to cannibalize some equipment from the ship and also to make use of the hydrazine fuel to extract the necessary components to produce water in order to grow his legendary potatoes. However, what Weir didn't realize at the time that he wrote the novel, although many scientists were beginning to suspect this, that water is actually quite abundant on Mars. There's a lot of water on Mars, and this should come as no surprise to anybody because there was a time when Mars had abundant water all over the planet, including very large lakes or possibly shallow seas. And although many scientists for a long period of time believed that the vast majority of the water, except for some subsurface ice at the poles, had evaporated out into space, it turns out that this is not the case at all, but rather a lot of these shallow seas appear to have retreated underground and remain in the form of abundant ice formations tantalizingly beneath the surface, and any expedition to Mars would definitely try to make use of this ice. However, in spite of recent discoveries, many planetologists continued to cling to the idea that water ice on Mars could not have survived at the equator, where evaporation should have been the most significant. But as time has gone on, we have discovered that there's actually a significant amount of ice even in the equatorial regions, both in the region of the Valles Marineris, a recent discovery made by the European Space Agency on that one, an enormous amount of water ice available, and now an even bigger water reservoir has proven that our beliefs about Mars could not have been more wrong. The Martian seas may be gone today, but the potential for new Martian seas are still there. There's enough ice in this one formation alone to submerge the entire planet to a depth of over 3 meters. Or to put it another way, there's enough water in this one area to support a colony of over 1 billion people. Good afternoon, viewers, and welcome to another Angry Bulletin. Again, we are going to be talking about Mars, a topic that I talk about with great frequency on this channel because it looks like, with any luck, that we're going to be at least exploring this planet inside of the next couple of decades, and if Elon Musk gets his way, colonizing this planet before the 2050s. And if this does indeed happen, well, we obviously need to know if the planet is actually capable of supporting human life, if a self-sustaining colony can be established on Mars without requiring regular resupply runs from Earth. All of that would be ridiculously impractical because Earth and Mars are not even properly positioned for resupply runs any more frequently than once every 2 years. Every now and then, sometimes a run might be sent from Earth to Mars utilizing Venus as a flyby option when Mars and Earth are on opposite sides of the sun, so you might be able to carry out an extra flight here and there, but overall, Mars needs to be able to sustain itself. If humans want to live there for the long term, resupply runs from Earth are just not going to be a practical option. So if that is indeed the case, and we want to not only have a small research station there with a few people or something a lot less ambitious than what Elon is talking about, well, we need to know that there's enough in situ resource utilization potential on this planet in order to sustain human life. And well, fortunately for future Mars colonists, it appears that Mars has everything they need, not only in terms of water and therefore breathable oxygen and also the potential for large-scale greenhouses, but also in terms of the soil. Granted, right now, Martian soil is not very well suited to any sort of planting activities or growing anything in it. It's a very toxic soil full of things called perchlorates, which are poisonous to humans. And if you were to grow anything in this soil, and by the way, that would be a difficult thing to do anyway, any of the produce grown in Martian regolith would also be poisonous because of these perchlorates. However, if there's enough water present, if you have lots and lots of water to spare, what that means is you can rinse out the perchlorates if necessary. You can treat lots and lots of soil before you start actually planting anything in it. Or you can simply utilize growing methods that don't require soil, hydroponics, aquaponics, those sorts of things. Aquaponics perhaps being one of the most attractive solutions because it requires the presence of fish in order to be successful, meaning that you would take fish eggs on a trip to Mars. Those fish would hatch in Martian water. They would fertilize the plants growing in the aquaponic solution, and the produce that you can get out of an aquaponic system is truly impressive. I've seen it done on a very large scale, and I'll tell you, the produce that you get out of an aquaponic system is really awesome. And not only that, you get fish out of the deal as well. So water is the key. And you don't just need some water, and you need a lot of it, and you also need it to be easily accessible. Well, it turns out that recent discoveries have indicated that Mars not only has water, and Mars not only has water in easily accessible locations, but it has enough of this water to support not just millions of Martian colonists, but 1 billion at least. Mars may be hiding an enormous stash of water beneath a region of Mars called the Medusa Fay Formation near its equator. This ice-rich deposit could be the largest known water reservoir in this part of Mars, with an estimated volume comparable to Earth's Red Sea. If melted, it has the potential to flood the entire planet in 3 meters of water, according to scientists. Fresh data from the Mars Advanced Radar for Subsurface and Ionospheric Sounding System, which is also known as MARSIS, suggests that the underwater water reservoir extends up to 3.7 kilometers deep, far deeper than previously thought. Quote, "We've explored the MFF again using newer data from Mars Express's MARSIS radar and found the deposits to be even thicker than we thought," said Thomas Walters, lead author of the study and a scientist at the Smithsonian Institution. Quote, "Excitingly, the radar signals match what we'd expect from layered ice, similar to Mars polar ice caps. The Medusa Fay Formation, and from here on out we'll call it the MFF, has long intrigued scientists due to its size and unusual composition, stretching for hundreds of kilometers and rising to over 1.5 kilometers high in places. It marks the transition between Mars' northern lowlands and southern highlands. The formation has been a focal point of scientific debate, with theories ranging from it being a massive accumulation of wind-blown dust to layers of volcanic ash or sediment. Early observations suggested that the MFF contained ice, as radar scans revealed a structure both transparent to signals and unusually low in density, but alternative explanations persisted until now. Researchers now believe that the MFF plays a crucial role in shaping the Martian environment. Its dust-rich deposits, which have been sculpted by wind into striking ridges, have been influencing the planet's atmosphere for millions of years. And by the way, these ridges can be as high as a 15-story building, providing a great shelter location for future Martian colonies. Scientists suspect that underneath this layer of dust lies a vast store of ice. Quote, "This latest analysis challenges our understanding of the Medusa Fay Formation and raises as many questions as it answers," says Colin Wilson, ESA project scientist for Mars Express and the ExoMars Trace Gas Orbiter. How long ago did these ice deposits form, and what was Mars like at that time? If confirmed to be water ice, these massive deposits would change our understanding of Mars' climate history. Any reservoir of ancient water would be a fascinating target for human or robotic exploration. But what does this mean for future Mars missions? Well, Mars poles contain vast ice reserves, but their harsh terrain, and especially low temperatures and energy challenges, make them unsuitable for human landings. As scientists prefer landing crewed missions near the equator, the discovery of equatorial ice will offer a strategic advantage to scientists, engineers, and also future colonists. Water on Mars could be used for drinking, oxygen generation, and even fuel production, reducing reliance on Earth-based supplies. Quote, "The MFF deposits, buried under extensive dust layers, remain out of reach for the time being," said Colin Wilson. Yet each discovery of Martian ice enriches our understanding of the planet's hydrological history and current water distribution. Beyond its role in exploration, the discovery offers new insights into Mars' past climate. The presence of deep equatorial ice suggests a drastically different environment in the planet's history. Scientists believe the MFF's ice, protected by layers of dust or ash, could reveal clues about Mars' ancient water-rich past. In other words, once again, we were wrong about Mars. But what does this mean in terms of in situ resource utilization? How important is this ice really? Well, 20 years ago, a team of researchers at NASA JPL set about answering that question in detail. And let me tell you, the numbers they came up with really tell the story. First of all, they analyzed 6 different methods of producing propellant on Mars, which will be necessary if we want to get back from the red planet. There's very few ways that an expedition to Mars can get there and back without having to refuel at some point. The 6 different methods were as follows. Number 1, electrolyze Mars water. In other words, we're assuming there is water available on Mars, just electrolyze it and produce hydrogen and oxygen for hydrolox propulsion. Then you have a Sabatier electrolysis utilizing Mars water as well, and also CO2. With this method, you produce methane and oxygen atoms. And by the way, this is the method that Elon Musk wants to use, and soon you're going to see why it's so effective. Then you have the Sabatier electrolysis method if you have to bring hydrogen from Earth. This also produces methane and oxygen, but the process is a lot less efficient. Then you have a reverse water-gas shift utilizing hydrazine. This only produces oxygen and no propellant at all, so not a very good solution. Then a solid oxide electrolysis system, also assuming that there's no water available on Mars. Again, all this produces is oxygen. Then if you combine methods 3 and 4, that is to say the Sabatier electrolysis bringing hydrogen and the reverse water gas shift, there's a solution involved with that as well that produces methane and oxygen. And finally, combining methods 3 and 5, Sabatier electrolysis with hydrogen brought from Earth and solid oxide electrolysis, that also produces methane and oxygen. Whew! Okay, lots of different methods, but which one really works? Well, interestingly enough, even though electrolyzed water is the simplest system because it doesn't require that you extract CO2 from the Martian atmosphere, it does require that you store the hydrogen, and that is a very difficult and expensive thing to do that requires a lot of mass and a lot of power. Interestingly enough, it turns out that method 2, that is to say the Sabatier method utilizing Mars water, is the most efficient way because it's easier to store methane on Mars than it is to store hydrogen. So let's have a look at the power and mass requirements of each solution. First of all, electrolyze water. Doesn't require a lot of power for chemical conversion, but look at that propellant storage requirement, 21,398 watts, meaning that the entire power required is over 24,000 watts, and the mass of the system is over 2 metric tons, whereas the Sabatier electrolysis method, again making use of Mars water, yeah, it requires that you get CO2 out of the atmosphere, but as you can see, the propellant storage requirements are tiny, 848 watts, and the balance of the system being 187 watts, meaning that the total power required for this solution is only 2,058 watts, and the mass of the power system is only 206 kilograms, a fraction of every other solution that you're looking at in this chart. It's very clear as to why Elon Musk decided to go with methane-powered engines for Starship. And I'm sure most of you have noticed that methods 4 and 5 also don't require a great deal of power or mass, but here's the difference. Those methods only produce oxygen, no propellant whatsoever. You have to combine those methods with one of the other methods in order to produce propellant at all. Again, option 2 is so much better. But let's go ahead and convert these numbers into how much mass you save for the trip to and from Mars using all of these different methods. Again, interestingly enough, the least amount of savings is by electrolyzing Mars water only. And that, again, is because of the enormous amount of mass and power required to store the hydrogen. But again, method number 2 saves so much more mass than any other solution. We're talking almost 155 metric tons saved by using this method. Again, very clear as to why Elon Musk decided to use a methalock solution for his Starship, a rocket designed for Mars colonization. So if this solution is the best way to produce propellant, it's also the best way to produce other things that are going to be useful to Mars colonists. For example, this electrolysis Sabatier method produces a great deal of excess oxygen and obviously drinking water. And on top of that, water is probably the best radiation shield available to astronauts. As a matter of fact, it's commonly used in nuclear reactors here on Earth as well. A couple meters worth of water provides almost complete protection from most types of solar radiation and cosmic rays, meaning that you don't need lead, you don't need tons and tons of concrete. All you need is water, or perhaps even better, water ice. One particular Mars habitat solution that I'm quite fond of is called the Mars Ice House, that involves a couple of meters of ice, providing not only structure, not only access to natural light that can pass through the ice, but also a lot of solar radiation protection. More than enough for the colonists on Mars. More than enough to completely eliminate what many skeptics of Mars colonization refer to as the big stopping point, the big stumbling block that will prevent Elon Musk or anybody else from colonizing Mars in the future. All of this lethal radiation. Well, once again, these habitats provide complete protection from that, and as I've mentioned in other videos in the past, the radiation at the Martian surface is not nearly as nasty as some people would have you believe. You could live 10 years unprotected on the surface of Mars and still only have a slightly elevated chance of contracting cancer sometime in the future. And again, this is completely unprotected, and no Mars colonist would go unprotected from radiation in the first place. So if this reservoir, this one reservoir in the Medusa Fay contains trillions of tons of ice, as it is likely to do, that being the case, 1 billion colonists on Mars is not an impossibility. It's very doable. Certainly it would take time to transport all those people to Mars, but Mars definitely has the potential to become a second home for the human species. And by the way, if you want to learn more about how Mars ice can be used to create greenhouses and other resources for humans in the future, well, I've got a much more in-depth video on the topic in my Patreon library. All the details are in the description. So there you have it. And really, we should not be terribly surprised that Mars has the potential to become a very habitable planet, one of the most habitable planets in the solar system, simply because this planet at one time was habitable, at one time had a breathable atmosphere, at one time had massive lakes and probably even shallow seas. All of these things existed on Mars, and there was probably abundant life to go along with it. Life that probably still exists today. In my opinion, it is the Martian life that's going to be the problem, not the absence of the necessities that human beings require in order to survive. Because as we saw in the video, if you have water, you not only have breathable oxygen, you not only have drinking water, you not only have produce, you also have a fantastic radiation shield. Everything you need to survive on Mars is located just a short distance beneath the surface of the red planet. And as long as we find an effective way to go get it, to go mine it and exploit it, as long as all of this becomes possible, and it does seem that our technology is more than advanced enough to make all of this happen, then the future that has been predicted in shows like For All Mankind, which I've been binge watching lately again, well, science fiction may become science fact before the end of the 21st century. Thank you very much for watching. Please don't forget to like and subscribe, and also please consider supporting this channel on Patreon and PayPal. I'm going to be heading to the National Archives at the end of this month, thanks to your support, and also I'm going to be returning to the UK. All of these things, you guys make it so much easier with your support, so please check the description for ways to keep this channel going. And as always, stay angry about space.